My name is Giovanni Fortese. I'm a PhD student of the University of Parma. The title of the paper I'd like to present you today is Improved Zinc-based coatings for ipersandelin technologies. In the present paper, the mechanical behavior of ipersandelin steel plates improved by zinc-based coatings is analyzed. In particular, two different types of coatings are considered. The first one consists in a zinc-based coating with addition of zinc. The second one consists in a zinc-based coating with addition of aluminium, zinc, and copper. My presentation is structured in the following section: an introduction of the hot dip galvanizing process, a description of the experimental campaign, a description of finite element model, presentation of numerical results and comparison with experimental ones, and finally conclusion. The hot dip galvanizing process represents one of the most common techniques used to protect metallic components, in particular those made in iron-based alloys, against corrosion. It consists in creating a zinc-based coating over the component to be protected, in order to preserve their aesthetical and mechanical properties for the time. The interdiffusion phenomenon between iron atoms of support and zinc atoms of a melting bath generates multilayer coatings named intermetallic phases, which can have different thickness, mechanical properties, and iron-zinc ratio. Traditional hot dip galvanizing bath usually contains lead that increases the fluidity of the bath, but at the same time can be very harmful for human health. Therefore, lead can be replaced by different metallic elements in order both to obtain the requested bath fluidity and to give different and specific properties to the coatings. For example, an increase in mechanical strength or the resistance against corrosion. Influencing the intermetallic phases formation and growth, which can be different from those of a traditional zinc-based coating. Regarding the experimental campaign, prismatic specimens extracted from two different hot-rolled ipersandelin steel plates were analyzed. Such ipersandelin steel plates are named the following: base 1 and base 2. After a particular pretreatment, specimens were galvanized into two different baths. In particular, a bath consisting in a traditional zinc-based coating with addition of tin, in the measure of 3% in weight. The corresponding series of specimens are named series 1, the following. And a bath consisting in a traditional zinc-based coating with additions of aluminium, tin, and copper in the measure of 5%, 1%, and 0.5% in weight, respectively. The corresponding series of specimens are named series 2 in the following. For each of the above series, 3 different dipping times equal to 60, 180, and 360 seconds were considered. Then, the analysis at optical light microscope showed the presence of two common phases in this series. In particular, a delta phase, located in the inner zone of the coating, characterized by high content of iron, generally from 7 to 12% in weight, and delta phase, located in the outer zone of the coating, characterized by a low content of iron, less than 5% in weight. Specimens of series 1 show even an intermetallic phase, located between delta and theta phase, which is named theta phase, characterized by a content of iron equal to about 5 or 6% in weight. Specimens of series 2 show instead a third phase, located between delta and theta phase, which is named lamellar phase, and whose chemical composition is still under investigation. Depending on dipping time, the intermetallic phase thicknesses change. As is shown in the table here plotted, it can be noted a higher activity of melting bath with additions of aluminium, tin, and copper, highlighted by thicker phases of series 2 specimens, respect to those of series 1 specimens. In particular, when the dipping time for such specimens is equal to 360 seconds, total thickness of coating represents about 30% of total specimen thickness. Therefore, intermetallic phases can considerably influence the mechanical behavior and the bending strength of specimens. each series of specimens, experimental bending tests were performed by employing an electromechanical non-standard device shown in figure on the right-hand side. Such a device doesn't allow specimens to roll, minimizing the interaction with supports, and ensures a constant bending moment in all the sections of specimens. Experimental results related to the above bending test are here shown in terms of bending moment against half bending angle for each considered dipping time. As can be observed, decreasing dipping time leads to higher bending moment values, and such effect is more pronounced for series 2 specimens due to their higher battery activity. Finite element model is proposed in order to numerically simplify bending behavior of specimens. In particular, considering the hypothesis of plane strain condition, a two-dimensional model with 4 nodes, plates, finite elements is employed. Due to the symmetry, only 1/2 of specimens is modeled. And in order to adequately simulate the experimental boundary condition, the following ones are considered. For nodes along x2 axis, displacements along x1 axis, and rotation around x3 axis are taken equal to 0. And for nodes along the opposite extreme, rotation around x3 axis is applied by increasing half bending angle from 0 to 35 degrees by considering a suitable interval angle. Here you can show a zoom of the coating for series 1 and series 2 specimens. The mechanical properties of series 1 specimens are listed in the table in terms of elastic modulus, high and low yield stress, tensile and ultimate resistance. In particular, stress and strain curve related to base 1 corresponds to that of ductile steel, whereas elastic plastic behavior is assumed for both delta and theta phase. The stress and strain curve related to theta phase is assumed to be elastic plastic for dipping time equal to 60 seconds, and a different curve for dipping time equal to 180 and 360 seconds. Such time dependence curves are assumed in order to take into account the crystal distribution characterizing such a phase, leading to a non-oriented structure which strongly influences mechanical behavior and strength. The mechanical properties of series 2 specimens are listed in the table. In particular, the stress and strain curve related to base 2 correspond to that of cast iron, different from base 1. And the elastic plastic behavior is assumed for delta and theta phase. Nevertheless, theta phase affects mechanical behavior and strength only a little with respect to beta phase. Therefore, much lower values of both elastic modulus and yield strength are taken into account. The stress and strain curve related to lamellar phase is assumed to show an elastic plastic behavior for dipping time equal to 60 and 180 seconds, and a different behavior for dipping time equal to 360 seconds. In these three figures, comparisons between experimental and numerical results in terms of bending moment against unbending angle are shown for each considered dipping time of series 1 specimens. As can be observed, a satisfactory agreement between experimental and numerical results is found, especially in plastic region, which is for half bending angle values greater than about 7 degrees. Dashed lines represent a scatter band equal to plus minus 1 degrees, corresponding to the accuracy of testing device. For high values of half bending angle, it can be observed an increase in strength by increasing the dipping time. And analogous comparison is here shown for series 2 specimens. But in such a case, for high values of half bending angle, we will observe a slight decrease in strength by increasing half bending angle and dipping time. And now, let us move to the conclusion. In the present paper, the mechanical behavior of 2 different improved zinc-based coatings has been analyzed. Improving consists in addition of tin or of aluminium, tin, and copper to a traditional zinc-based coating. Firstly, experimental bending tests were performed by employing an electromechanical non-standard device, which ensures a constant bending moment in all the sections of specimens. Then, a finite element model is proposed in order to simulate the above mentioned experimental bending test. For the specimens with addition of aluminium, tin, and copper, a higher activity of melting bath has been observed, leading to higher bending moment values, but at the same time showing a slight decrease in strength by increasing half bending angle and in peak time. A comparison between experimental and numerical results in terms of bending moment against half bending angle seems to be quite satisfactory. Thank you for your kind attention.